My presentation will be about the Alveo MA35D video accelerator and its support in GStreamer. We focus on the latest additions that concern machine learning features available on the card. So, my name is Jakub. I'm working at Collabora on various multimedia projects since 2018, based in Czech Republic, Europe. So what is the MA35D? It's a media accelerator for applications that demand a high concurrency of streams. It supports accelerating of the full video pipeline from decoding to adaptive bitrate scaling, even some basic video effects and encoding all accelerated on the card. Supports H.264, H.265 and AV1 for encoding and decoding. Also there is some support for decoding via VP9 and JPEG. It can give you up to 4 different 4K streams at 60 FPS for H.264, 5 and AV1, and it also features a separate engine for AV1. So in that case, you can go up to 8 4K streams. If you want to do some lower resolution like 1080p, you can do parallel 16 streams and so on. So the card also features a dedicated AI processor that can perform inference on the video frames. It can potentially execute multiple different machine learning models. In the current preview, there is one model that is a region of interest that is able to detect faces and text in the video frames. More models are still to come. And the output of the engine also can now help the video encoders on the card to achieve better video quality during compression. So the current revision of the SDK is version 1.2. And it comes with a set of GStreamer elements that expose the capabilities of the hardware. The first group is just the encoders and decoders, AV1, H.264, H.265 JPEG. Then we have MA upload and download elements that deal with transfers of the video frames from the system memory to the memory of the card. And there are also a sizable number of video effects that are available in the hardware, rotating the image, scaling, even compositor. And what I've been working recently is adding a new set of elements that will allow these AI features and executing the ROI filter region of interest. So you can have a look at them. The first of the new elements is AMA ML ROI. This is the element that actually executes the machine learning model. Its input is a video frame in 1080p or 720p in RGB format that first needs to be uploaded into the hardware using the AMA upload element. There are 2 flavors of the filter available, either detecting faces or detecting text. So the input video frame leads to the copy or the same frame on the output. And as an attachment, it has a sideband data with the result of the filter. Here, some detected faces. The format of this map is a grayscale map that where every pixel represents 16 by 16 region in the original video, and it's one byte value that where higher value indicates there is an detected ROI region. Sideband data, this is a hardware feature of the card. This is still all happening on the card. But what if you want to inspect the result of the inference yourself? Then you can use the AMA download element, and it will convert you that frame in the card into the system memory, and the hardware-specific site data will be converted to GstAnalytics relation meta attached to that frame. This is not required to do when you want the result of the inference to be used by other AMA elements, but here is some example how you could access those data in the analytics meta using your own element that you could write, just getting the meta out of the buffer, and then you would iterate through the relation meta of the type object detection, and every object detection instance represents one of those 16 by 16s regions in the output of the ML filter. Here you can, for example, print out the confidence level of that region. In the original sideband data, it's 0 to 55. Here it is converted to 0 to 1, as it's standard for the analytics object detection meta. So it kind of works, but it's pretty ugly, I would say. But this is what is currently available in GStreamer. But there is also a better way to represent such data in GStreamer, because output of the ROI filter is a tensor. We could use the GST tensor meta that is currently private to the Onyx plugin, but there is some effort to make it public API that is part of the analytics. And then you could just, instead of all the work with the analytics meta, you could attach the tensor meta, which would entail just copying the tensor data from the hardware to a GST buffer, and setting some data type which is unsigned byte, and the number of dimensions is 2, and this array would contain the dimensions of the output data. Okay, so now you don't want to inspect the data yourself. You want to use that to improve your video encoding. There is another element here for it, AMA ROI scale. Its input is your video frame in the original intended resolution that you want to encode, and the other up to 4 inputs are the outputs of the ML ROI element. These are fixed at 1080p or 720p. 720p is preferred and this element will scale the output of the filter to your intended resolution. If there are more than one inputs, it will merge them together, and it will convert the object detection to a delta QP mag that can be fed into the AV1 encoder, and it will aid in better encoding. As an example here, original image without object detection, and here with ROI enhancements, the faces retained more detail thanks to the object detection done previously in the pipeline. So some example pipelines. First one, some basic transcoding scenario where you want to take some video in a higher resolution and downscale it. So you need two inputs to feed your ROI scale. So there is AMA scaler element for it that can do video scaling and also pixel format conversion. So it will give you your original or image that you want to encode, and the other output of the scaler will be fed to the ROI filter here in face mode, and here in the ROI scale the inputs will be combined, converted to the DQP sideband data, and the encoder will use them to improve the encoding. AMA scaler can produce several outputs at a time, not only two. So, for example, here you can have some live source webcam. In this case, you have to upload the frames into the memory of the MA35D card. And after this, you can produce several resolutions, and you will have just one input to the ML ROI, and every resolution that you want to create will need its own ROI scale, and so you will use the element to feed both of them, and then it works as previously. Conversion to the QP sideband data and encoding. You can save it to file or stream it through WebRTC, whatnot. Yeah, here we have the pipeline of the previous example. If you want to run multiple different ROI filters at one time, it's also possible either in a parallel mode, where you will feed the output of the scaler in parallel to two different models. Here, one is detecting faces, the other one is detecting text, and then both of those inputs can go to one ROI scale and affect the output of the encoder. Again, the pipeline, and another possibility is to use two different models in serial. In that case, each one of them will attach its own sideband data to the frame, and the ROI scale will merge them again together, and this will result in another encoding. Okay, the source code, the GStreamer integration of the card is available as an open source, dual licensed. It's available to download from AMD's GitHub. as a zip file. Currently, all the elements except these two ML elements are available there. These two will become available in the next release after they are stabilized. Okay, thank you. That's all for my talk. And if you have any questions, now we have time. No, thank you.
You mentioned that, okay, this is the hardware has the text spaces, and then it encodes spaces better, I guess. Kind of going more into the second part. What does it actually do with the data? How does it focuses on encoding? Please repeat the question to the participants.
So the question is how the actual conversion from the ROI data to improving the encoding works. So I had that one slide here. This will convert the ROI data that are just detected objects to dynamic QP sideband data that can be fed to the AV1 encoder, and that encoder will just use this data to put more bandwidth to the areas where the objects were detected, so you will retain more detail, whereas other areas of the image don't need to be affected. Is this answering the question?
Or is this a custom thing for?
This is all happening in the hardware, so it's a custom thing that can be used only here in the AV1 encoder.
You mentioned that the video could be sent out via WebRTC. What is the latency of the whole processing, and how fast does it adapt to bitrate changes?
This hasn't been tested in the wild yet, but the latency of the whole pipelines in the hardware could be in like 10 milliseconds.
So quite low. And how fast does it adapt to bitrate changes? Because this is a big problem with many AV1 encoders.
There is no adaptation at this point.
Okay, thanks.
Hi, just a question in fact, in this slide, you mentioned that you're changing the pixel format, the surface to RGBP before you do the inference, which you use for then, increasing the bitrate and making it higher resolution at the objects. So why go for RGBP? Wouldn't inference already be a significant latency adding step? So I'm just curious about why would you choose a higher density pixel format there?
That's how it's implemented in the hardware. That's more question for AMD, why they implemented it this way. That was a requirement that input of that particular filter is RGBP. Okay. And in future, there will be more advanced filters, perhaps, so you will be able to use another pixel format.
Okay, thank you.
So I have a question about the ROI element. Are the face and text model the only one available, or can we add more?
Yeah, it's not currently supported in GStreamer level, but the models don't live in the hardware; they are loaded from a file. So in theory, you could create your own model that could be executed here, but you would have to go to some lower layer of the middleware libraries, not currently on GStreamer level.